The modern hospital ward relies on thousands of interconnected devices. Monitors, pumps, and sensors all share a continuous stream of physiological data. This density of medical IoT devices allows for remote monitoring and automated patient care. It also creates a massive, decentralized attack surface. Routing all this data to a centralized cloud for security checks creates strict communication latency. The sheer volume of traffic overwhelms standard bandwidth, slowing down life-critical decisions. This is where the Smart Healthcare Cyber-Physical System, or SHCPS, comes in. It combines physical medical hardware, real-time physiological sensing, and a dedicated computational network. To protect this system, security cannot live entirely in the cloud. It has to move to the physical edge of the network. This architecture relies on two distinct defensive layers working locally: edge-based virtual firewalls and deep learning algorithms designed to cleanse data on-site. Protecting medical IoT devices requires isolating threats at the local source, eliminating the delay of cloud-based threat detection. The physical foundation of this architecture begins with the patient. Decentralized sensor nodes are distributed directly across the individuals using the system. These devices gather highly sensitive physiological data. This includes vital signs from implanted biosensors, flow rates from oxygen concentrators, and rhythms from heart pumps. Instead of sending signals to a centralized cloud, data is routed locally. As seen here, wireless sensor nodes on the body transmit directly into a localized edge gateway. This data dictates life or death interventions. Therefore, the gateway processes signals on-site, completely removing cloud communication delays. Processing data locally at the edge translates directly into immediate physical action. Medical robotics can respond to patient needs the moment a signal drops. For example, a universal robot, known as a UR5, receives real-time item detection data from edge cameras. It instantly physically retrieves medical supplies. It executes this action without waiting for a cloud server to approve the command. The edge gateway's primary function is speed. It aggregates data and eliminates the network latency that would otherwise stall critical physical interventions. With the data localized, the system needs a first line of digital defense. This is the virtual firewall and intrusion detection system. Rather than waiting for data to reach a central server, these security protocols are deployed directly at the mobile edge networking layer. This diagram shows the network topology, placing the firewall at the exact point of interception. It acts as a gatekeeper before traffic routes upward. Sitting between edge applications and the broader network, the firewall immediately catches obvious malware, inspecting raw traffic before it propagates. This localized inspection offloads the heavy processing required for security from the small, individual medical devices. It physically isolates malicious packets early in the transmission chain. Historically, firewalls were physical pieces of hardware. In this virtualized environment, they operate as software hypervisors running directly on the edge nodes. Filtering traffic at the edge ensures the encrypted cloud database only receives clean baseline packets. Contaminated data never reaches the central storage. A standard firewall blocks known malware signatures, but struggles with obfuscated data from fake user profiles. This requires a second layer of defense. Any raw text strings, metadata, and images entering the healthcare system must pass through a strict pre-processing pipeline to strip away noise and malicious formatting. The algorithm normalizes the data in 3 steps. It restores contracted words to their formal state. It converts all uppercase letters to lowercase and completely strips out unique symbols and embedded URLs. With the text normalized, the system mathematically analyzes the user profile to detect fake identities. It does this by measuring string similarity. This is the Jaro distance equation. It calculates the exact mathematical variance between 2 character strings, like comparing a submitted username against a database of known real names. The system combines this calculated Jaro distance score with a check on the percentage of the user's profile that is actually completed. This mathematical cleansing strips out the noise. It provides a clean, standardized set of data points for the next stage of the architecture to analyze. The final layer of threat detection relies on a convolutional adversarial fuzzy model with an encoder neural network, or CAF-ENN. This diagram breaks down the architecture. First, the input data is scaled to a precise 256 by 256 by 3 tensor. It passes through the initial convolution layer. Next, the data hits the max pooling and leaky ReLU activation functions. These layers filter the output. The pooling layers intentionally decrease the resolution of the feature map. This prevents the model from overfitting to useless noise and extracts only the highest value abstract features. Finally, the condensed data vector enters the fully connected layers, which contain 4,096 individual neurons. This structure processes the final prediction. The model is refined using adversarial training. A generator creates simulated attacks, and a discriminator attempts to catch them. The system trains itself until genuine medical data mathematically scores higher than synthesized threats. The CAF-ENN operates as a high-speed filter. It takes the clean, pre-processed data streams and outputs a definitive real-time binary classification, safe or threat. The complete smart healthcare cyber-physical system relies on layered defense. It integrates physical edge sensors, localized virtual firewalls, and neural network data cleansing into a single pipeline. To test this architecture, researchers ran the deep learning model against diverse datasets containing simulated CPS-based fake user attacks. This visualization shows the final performance metrics from the study. The system achieved 95% accuracy, 83% precision, and 73% recall. An accuracy rate of 95% proves that the model successfully isolates advanced cyber threats, and the localized architecture ensures this happens without delaying real-time medical robotics. In a medical ecosystem defined by thousands of decentralized IoT devices, routing all data to a central cloud for security checks creates an unacceptable bottleneck. Protecting patient lives requires moving computation to the physical point of care. Defensive neural networks must verify physiological data at the absolute edge.